Hello everyone, welcome back to Civil Learning Online YouTube channel, and this is fifth lecture on Laplace transformation. And till now we have studied about some basic formulas which are required for solving the numerical based upon the Laplace transformation, and also about when the given functions, trigonometric function, are in product form and how we can remove the product formula because we cannot operate the trigonometric function which are in product form, and there are some special formulas we have discussed about that also. And we have even discussed about the function which are multiplied by t to the power n in the previous lecture, that was lecture 4. You can access to those video either by moving to the playlist or through the link which is provided in the description of this video, and you are free to write me on my email address, that is civillearningon@gmail.com, which is also provided in the description. And without any further delay, let's continue this lecture. So here we will continue the concept of Laplace transformation, that is division by t to the power n, and I have selected two numerical equations that are e to the power at minus cos bt divided by t, 1 minus cos t divided by t square. And whenever we face the problem in which we see the functions which is divisible, which is in the division form by t to the power n, we have to operate it using the concept. So one thing more guys, for division we will come to face the problem which is we can operate only once. If there is power t to the power n, means if there is t, then we can find a Laplace transformation one time. If there is 2, then we have to find the Laplace transformation in second step, and similarly if there is 3, then we have to find the Laplace transformation third step, which will be cleared using the numerical example, that is second numerical example in this video. That concept will be clear. So let us just take it as division by t. So if we have Laplace transformation of f t equals to f p, if it is true, then what happens? Laplace transformation of 1 upon t times f t will be equals to integration from s to infinity f s with respect to s. We have this condition. So now let us move toward the solution of the numerical problem. So the first question is, question number 1 is again e to the power at minus cos bt upon t. So write down the solution here. So on writing the solution, we know that the Laplace transformation of e to the power at minus cos bt will be given by, Laplace transformation of e to the power at will be given by 1 upon s minus a. If here it is plus, then if e to the power at is in plus, means if exponential has power positive, then here we take negative sign. If here it is negative, we take positive sign. So here it is positive, so we will have s minus a. You need to watch the first lecture of this series for getting this formula. So we have minus cos bt, means cos bt formula will be s upon s square minus b square. Okay, now Laplace transformation of 1 upon t times e to the power at minus cos bt will be given. We need to use this condition now, so we have to integrate these terminologies. So integrate from s to infinity, lower limit s, upper limit infinity, integrate 1 upon s minus a minus s upon s square minus b square with respect to s. Now see guys, we know that in integration of 1 upon x equals to 1 upon x with respect to x equals to log x, and it says that integration of derivative of a given function means with respect to x will be log of that function. I hope you understood. Whenever we are asked to find the integration of a term and that term is in fractional form and it carries the numerator, if its numerator is the derivative of its denominator, if its numerator, see the derivative of x is 1. So what I said, if we are integrating any term and its numerator means the upper portion of the fraction is derivative of the denominator, means derivative, it is this x is carrying its derivative as numerator. So in that case what happens, its integration will be log that function, log x. That same will be the case here. See here, derivative of s minus a, if we find the derivative of s minus a with respect to s, what will have here, derivative of s minus a will be 1. So we can see that in the first term, this is first term, this is second term. So in the first term we have the derivative of s minus a, it is carrying its derivative itself. So here the derivative of this term will be log s minus a. Why so? Derivative of a will become 0 and derivative of s will be 1. So derivative of s is 1 and derivative of a is minus 0. So it will be automatically 1. So it is log minus a, log s minus a. Similarly, you can see here derivative of s square, derivative of s square will be 2s, derivative of s square minus b square with respect to s will be 2s, because b is constant here, so it will be 0 and derivative of s square is 2s. So here if we add 2 and divide it by 2, then it will again be again get into the log form. So we will do the same here. So minus 1 by 2 log s square minus b square times d. We have already integrated, so we will simply put the limit here, that is from s to infinity. Now let us solve this step further. So we can rewrite it as 1 upon 2 times 2 log s minus a minus 1 by 2 log s square minus b square and the limit, that is from s to infinity. Now guys, you can see here, whenever we have m times log n, we can rewrite it as log n to the power m, means this multiple coefficient will become the power of its n. So we have here this, we have rewritten is log s minus a as 1 by 2 times 2 log s minus a, so that we will cancel out the s square in both the terms. So for that reason what we will do, let's take 1 by 2 common from both the terms. So we will have here log s minus a whole square and minus log s square minus b square and limit, that is from infinity to s. Now we have 1 upon 2 and log, let's take s common from here from this term. So we will have here s square times 1 minus a upon s and this square. What I did here, I just took s common from both. Here we have s, but here s is missing, so what I did here, just multiplied it by s and divide it by s. So we have taken s common from both. So on taking s common, and this due to this power it will become s square and bracket, and this here it becomes 1 minus a upon s and this whole square, and this is in, and one thing more, what happens when log m minus log n, it becomes log m upon n. That is what I have done here, that is log a or log m minus log n. So log m upon log n, n is s square, again take s square common from here, so s square 1 minus b square upon s square, and put the limit infinity to s and close the bracket here. So cancel out, s square gets cancelled out. Now proceed further. Now what we will do here, see 1 upon 2. Now it's time to put the limit here. So limit, when we put limit, what we do it as a minus b. Let me use another page. So we have here, suppose we have log b and our limit is x and y. So first of all, what we will do, we will put upper limit. In place of b we will put x minus log y, and same will be the case here also. We have, in place of s we will put u infinity. So something by infinity will get 0 and log 1 is equal to 0. So here on putting infinity here, something by infinity is 0, 1. So and here also something by infinity is again 0. So log 1 we will ultimately get upper limit as, upper limit will give upper limit is infinity. So on putting infinity it will get 0, because log 0 is equal to, log 1 is equal to 0. So 0 minus log, now time to put lower limit. So in place of s we will put s. So we will get the same thing, that is 1 minus a upon s whole square divided by 1 minus b square upon s square, and we have put the limit already, so simply put the bracket now. So we will have here minus 1 by 2 log. Now we need to remove the denominator, which is s. So we will have here s minus a square upon s square minus b square. Why so? See here, we have here, we can rewrite it as, see here what happens here, 1 minus a upon s whole square. So what happens when we take here, it is nothing, means 1, and we have to multiply. So on taking the LCM we will have here numerator as s and denominator will be s minus a, and this is whole square, means this square and this square upon s square. Here nothing, means 1. So s square numerator will be again, here also denominator is s square, and 1 times s square is s square minus b square, and this s square gets cancelled out. So we will get this s minus a square upon s square minus b square. This is the outcome of this term. Now there is one more concept, that is minus log a equals to log 1 upon a. So what happens here, minus 1 by 2 log s minus a square by s square minus b square will become, we can interchange to remove the minus sign here. So numerator will become denominator, denominator will become numerator. So we will have here s square minus b square upon s minus a whole square. This is our final answer. You can leave it up to here also, or you can proceed it one more step, that is up to you. But I hope you understood this method. What happened here, see here, let me show you with another example. See here, we have minus log a upon b. So what happens, this due to this minus we can rewrite it as log 1 upon a upon b. So on doing the reciprocal, what happens, log b upon a. That is what has happened here. We have removed in order to remove this minus sign, we have applied this theorem here. Now we will proceed toward the solution of the second example. So before solving this numerical example, I would like to recall you the concept what that was Laplace transformation of 1 upon t times f t equals to integrate s to infinity f s and ds. So you can see here this theorem is for only t to the power 1, but we have here t to the power 2. So how we will solve this? See here, watch this numerical very carefully, and this is very important from the exam point of view. So we have here, we know that Laplace transformation of 1 minus cos t is 1 upon s minus s upon s square plus 1. So Laplace transformation of 1 minus cos t upon t will be given by integration of from s to infinity 1 upon s minus s upon s square plus 1 ds. So again we will have here log s minus 1 by 2, it will get 1 by 2 and 2s, so 1 upon 2 log s square plus 1. That is the same concept what I did in the previous example, that when the derivative is numerator of the denominator, means if the denominator carries its derivative, then it will get the log form, and that is a rule of integration, and we have to put the limit from s to infinity. So see here again we have to remove this s square, we have to cancel out one s square so that we will be able to put this limit. So again we will do here 1 upon 2 log s, 1 upon 2 times 2 log s minus 1 upon 2 log s square plus 1, and in limit is from s to infinity. So we will take 1 by 2 common, so taking 1 by 2 common we will have here log s square minus log s square plus 1, and limit is from s to infinity. So again 1 upon 2 log s square upon s square plus 1 from infinity, from s to infinity, again 1 upon 2 log, take s square from common from denominator, so we will have here 1 upon 1 minus 1 plus 1 upon s square, and from s to infinity cancel out, so we will have here 1 upon 2 log, and we have 1 by 1 plus 1 upon s square, and limit is from infinity, from s to infinity. Now if we put the this upper limit and lower limit here in place of infinity, in place of s first we put infinity, so it will get something by infinity 0, and log 1 is 0, so we will have here 1 upon 2 and 0 minus log 1 upon this, due to this infinity here it will get 0, this whole log and this value will make it 0, and due to this s we will get the same, so we will get here 1 upon 1 plus 1 upon s square. So on rearranging it, we will get minus 1 by 2 log, and here it is in denominator, so s square plus 1 upon s square will get s square upon s square plus 1. So we have to remove this minus sign, so in order to remove this minus sign we will interchange the numerator and denominator, and why I have already shown you. So we will have here 1 by 2 log s square plus 1 upon s square, and this minus sign will get removed. Now what happened, we got the Laplace transformation. This is the value of Laplace transformation of 1 upon t times 1 minus cos t, but in the question we had 1 minus cos t upon t square. So Laplace transformation of 1 minus cos t upon t square will be equal to integration of s to infinity 1 upon 2 log s square plus 1 upon s square ds. So how we can find the derivative of this term? See here, we will take 1 by 2 common. So taking 1 by 2 common, we will have here s to infinity log s square plus 1 minus 2 log s ds. Now let's integrate by part. So by integration by part. Now let's understand what is integration, how we do the integration by part. So integration by part says that integration of u times dv equals to u times v minus integration of v times du. So here this whole is going to be u and this ds will be equivalent to dv. What I said, this our u will be u is equal to log s square plus 1 minus 2 log, yes, this is our u, and we will require the value of du also. So du will be log x derivative, log x derivative of this will be derivative of log s square plus 1 will be 1 upon s square plus 1 times 2s minus 2 times log x, log s derivative with respect to s will be 1 upon s. And guys, we have this 1 by 2 also. So our u will be 1 by 2 times this whole. We have this 1 by 2 also, so we will take it as a whole, 1 by 2 upon this. So we have we have to multiply. Now we are finding the derivative of this term, so we will multiply this by 1 by 2 and this 2 will also multiply this, so we will get this. So our final du value will be s upon s square plus 1 minus 1 upon s. And on solving this into the single term, then we will have here, let's take the LCM of numerator, then we will have here s times s square plus 1, and on numerator we will have this s will get multiplied with the remaining item which will have on LCM. So we have s, so this s will get multiplied with this numerator s, so s minus, and this 1 will get multiplied with this 1 will get multiplied with remaining item, that is s square plus 1. On solving this, we will get here s square minus 1 upon s times s square plus 1. So we will have finally minus 1 upon s square plus 1, and this is the value of du. And our v is, see here we have one more term, that is v. So on equating this, what I said, this I have considered this whole as u, and this 1 by 2 is also here, so this is whole u, and this ds in place of s we have v here, so we will have s equals to v. Now use this formula here, what I wrote here, that is integration of u times dv equals to u v time minus integration of v times du. So we will have here the u, our u is 1 upon 2 times log s square plus 1 minus 2 log s times, in place of v we have s, in place of b, you can see here in place of b we have s, so we will write here times s minus integration of b, in place of b we have s, so s times, and in place of du, we have calculated the value of du, that is minus 1 upon s square plus 1, and we have to put the limit also, so I will use the large bracket for putting the limit, and I will simply change this bracket to curly bracket, and we have to put limit from s to infinity. And here we have numerator, in place of numerator we have s times s square plus 1, so here we will have this s times s square plus 1, and this minus and minus will make it plus, and this minus and minus will get cancelled out. So I am going to write one more step here, that is 1 upon 2 and this curly bracket log s square plus 1 minus log, and it can be written as log s square and multiplied upon by s minus will get plus integration of 1 upon s square plus 1 ds. We have to integrate this, so integration is happening in terms of s, so it will get ds, and from s to infinity. Now see here we have one this s will come here, so we will have here s upon 2 log s square plus 1 upon s square. This term will get transformed into this and this plus, and we have integration of 1 upon s square plus 1. So integration, now I need to provide you with some formulas which are used for finding the integration, and they are integration of 1 upon a square plus x square dx equals to 1 upon a tan inverse x upon a plus c is constant. Similarly, integration of 1 upon a square minus x square dx equals to 1 upon 2a log a plus x upon a minus x plus c. Integration of 1 upon x square minus a square equals times dx equals to 1 upon 2a log x minus a upon x plus a plus c. So we can see that this we have to integrate this, so this is in the form of this, so we will have here 1 upon a tan inverse s upon, in place of a we have 1, so tan inverse s, and we have to put the limit from s to infinity. So tan inverse infinity is pi by 2, so we will have here s upon 2 log s square plus 1 upon s square plus 1 upon a times 1 upon a, in place of a we have 1, so this is 1, so we do not need to rewrite it. Okay, this is from formula. In place of a, in formula we have a, and here we have 1, so we will have 1 upon a means 1 upon 1, so it is 1, and tan inverse infinity is pi, tan inverse infinity, tan 90 equals to infinity, tan 90 equals to infinity, tan 90 means pi upon 2 equals to infinity. So in place, when we put this upper limit, then it will tan inverse pi means pi upon 2 minus tan inverse s, and this is our final answer. So we got this. So if I rewrite the answer, then we will have here s upon 2 log s square plus 1 upon s square plus pi by 2 minus tan inverse s. This is final answer. And if you guys want some extra example related to this form, that is division by t, then leave the comment in the comment section. I will add it, and we will continue with this Laplace transformation. And in the upcoming lecture I will discuss about the inverse Laplace transformation. And if you guys have any kind of confusion, any kind of problem, then you are free to write me at my email address that is provided in the description. See you in the next video. Till then, stay safe and take care of yourself, and do not forget to subscribe Civil Learning Online channel if you do not want to miss any updates.